Hello everyone, it's really my pleasure to present our paper about robot calligraphy there. The first thing I would like to say is robot calligraphy is a difficult but interesting task. At first, as is known, calligraphy is really a kind of beautiful art. It has been pursued by humans for thousands of years. However, it is also very difficult because generally it takes humans many years to practice to really master this kind of art form. Such great difficulty mostly comes from the writing tool, which is just shown by this figure. The tip of the brush is generally soft, and so that adds a lot of difficulty in the writing process. Such difficulty also makes controlling the robot calligraphy a very meaningful task because it will not only save human great effort, but also the successful control techniques could also be applied to many other related areas, such as soft robots. Currently, research in this area adopts either a learning-based method or an optimization-based method. Learning-based method is not fully developed in this area, and so we would mainly consider the optimization-based method. A central part for optimization model would be a virtual brush model, which is able to predict or simulate the behavior of the real writing brushes. A very complicated virtual brush model will make the optimization process and also the system identification part extremely difficult or even invisible. However, a very simple virtual brush model obviously won't do its job. And so in this paper, the main contributions that we want to introduce in this paper would be, at first, a novel virtual brush model, which is able to simulate the real writing behavior of the brushes. And secondly, we also propose an efficient optimization framework, which would work very well with our proposed virtual brush model. Here is the methodology. At first, the input into our writing system could be any character Unicode, and then we will give that input to our optimization process, and it will run optimization and give a writing trajectory for the robot to execute. After robot using the writing brushes finish the execution, we will get our final writing results. For example, just like this figure shows. Next, I will mainly introduce the two central parts of our paper, the virtual brush model and the trajectory optimization. We will take a look at the virtual brush model at first. The virtual brush model mainly has two components: the dynamic component, which decides how the brush parameters are updated during the writing process, and the drawing component, which shows how the brush leaves a writing mark on the paper if all of its parameters are known. In this slide, we will look at the drawing component. The brush parameters include, at first, end effector coordinates, which is shown in this blue dot, and also the orientation, which describes orientation of the writing mark in the real paper, in the virtual paper, and width and drag parameters, which describes the shape and the size of the writing mark, and finally offset parameters, which shows the distance between the writing mark and the brush holder. We will use standard X to represent the end effector coordinate and the Italian X to represent the connection of the brush parameters. And then it's about the dynamic component. The control signal is used as the end effector coordinates, and the state of the brush parameters are updated based on the current state parameters and the current control signal. Updating on the end effector coordinates are pretty straightforward. The width and drag parameters is a little abstract, and so we go back to the experiments, and we did a lot of experiments to try to find some relationships, and here is what we found. The width and drag parameters during the writing process, after we collected a lot of sample written mark, we found it has a very linear relationship with respect to the Z parameter, which basically describes how much the brush is pushed down during the writing process. And so we run a linear regression, and that gives the width and drag function. However, apart from it, we also found during the real writing process, the updating on the width and drag parameters are pretty smooth. And so further, we also introduce an inertial factor to the updating formulas to make our virtual brush model behave more similar as the real writing brushes. Also, we would like to introduce the concept of root point. The calculation of the root point is not hard. Given the end effect coordinates at first, we project it to the virtual paper plane, which is shown by this pi function. And then we move the projected point following the direction specified by the orientation parameters for a distance specified by the offset parameters. And then we will get the root point coordinates. There are also two things we would like to mention there. At first, offset is simply the distance between the root point and the end effect coordinates. And also orientation can be gotten if all the other variables are known in the definition formulas of root point. These two important observations will also become the main motivation for the updating process on the offset and orientation parameters. However, before finally introduce our two formulas, I would like you to take a further look at the writing process record. During this, although this is not the real writing process, but we can still see the main properties. And if you can notice, the tip of the brush does not always follow the movement of the brush holder. This phenomenon, in our opinion, has mainly two reasons. At first, obviously there is a friction between the brush and the paper, and that friction will have a tendency to stop the tip from moving. And also, secondly, the ink that the brush writes with is a special kind of liquid with high density. And so there will be a strong surface tension generated between the brush and the paper, and that force will also stop the brush from moving. Or in the simple words, after dipping the ink, the brush simply becomes sticky. So these two forces will stop the tip from moving only if the brush holder becomes far away from the tip, so that the tip must move, otherwise the tip simply breaks. And so such observation gives us the updating formulas for the offset parameters. We will use the function offset zi plus 1 to represent the maximum offset parameters possible at each time instance. And then this offset parameter function estimates after the brush holder moves to a new position its distance from the old root point position. If after updating the coordinates of the end effector, the distance between the end effect brush holder and the root point is still not larger than the maximum possible offset, we will simply say the root point, the tip does not move, and the offset is simply set as the distance between the tip and the brush holder. However, if such distance is bigger than the maximum possible offset, then we say the brush has moved far away and the tip must follow its movement. And then in that case, the offset is set at the maximum possible offset. And since the root point moves, we will say the root point is simply at the line between the old root point and the new end effect coordinates. After updating all of the parameters, we can use the inverse calculation formulas of the root point to get the orientation parameters. The maximum possible offset parameters is decided by collecting data and run a quadratic regression based on the offset parameters and the z parameters. Now, after introducing the virtual brush model, we would like to introduce the trajectory optimization part. The main idea is inspired from the pseudospectral optimal control method. And we use pseudospectral methods to parameterize the stroke trajectories. The basic idea can be shown by this simple example. Given a set of discrete blue points, we would like to find the polynomial curve to parameterize the trajectory of these blue points. And so a very simple and straightforward solution would be choosing convocation points, which are the red points in this figure, and then connected these red points by something like Lagrange or barycentric polynomials. And then we can use, in that case, we can simply use these red points as the parameters to represent these blue trajectories. And so we can apply this technique to the stroke trajectories, but before we would like to also introduce stroke extraction, because the reason is also simple. Running optimization based on individual strokes one by one is surely more efficient than running optimization directly based on the whole trajectory, whole characters. Stroke extraction can be achieved by many available methods, and this figure shows the stroke extraction process and the results. And so we can, and then now we are able to apply our slow spectral methods to the individual stroke trajectories. Also notice that stroke trajectories is really nice in a three-dimensional space, and so we need three sets of parameters to fully represent a stroke trajectory. And then finally, here is our optimization objective function. This V function represents the virtual brush model. XS represents a stroke trajectory parameters. And this IS represents the reference picture. So basically, the objective says that we want to find a set of brush stroke parameters so that the virtual brush could generate an image that's as similar as the reference image as possible. We also add some regularization term to make sure the brush optimization will not generate some crazy results. The whole optimization could be solved easily with the help of Narenberg-Makruda nonlinear optimizer. And the whole problem also requires some kind of initialization. As for the X and Y components of the stroke trajectories, we extract the middle line of each stroke or skeleton to parameterize it. The Z components is simply initialized at the constant value. The initialization process is shown in figure C, where the red line shows the initial stroke trajectories, and the black part shows the initial picture rendered by our virtual brush model. We also correspondingly design the process to dip the ink. By constantly dipping ink after the robot finishes one stroke, we provide the necessary ink to the brush so that it can constantly write something. And also, during the process of dipping ink, we can also make the tip of the brush restore to a very good state so that we can avoid the simulation error accumulate as more and more strokes are written. And finally, here are some results that we obtained with our method. Column A shows the reference picture, and column B and C shows the initial and final trajectory. Column D and E shows the initial and final optimized simulation pictures, and column F and G shows the initial and the final written characters. We can see that there are still a lot of improvements after optimization. We also further use some different kernels to show the error distribution. And we can see that after optimization, there is much kernel in the right column than the left column, which also proves the success of our whole optimization methods.